Hi everyone, welcome to this Math 111 video lecture on properties of logarithms. If you want a review of what logarithms are and how they relate to exponentials, you can check out one of the previous videos. But in short, a logarithm is a power, and also a logarithm is the inverse of an exponential. So when we talk about properties of logarithms, we're mostly using these two ideas, the fact that logarithms are powers and that they are the inverse of exponentials, so they undo exponential operations. And this idea is what motivates the properties of logarithms. So let's think about how linear functions work. Well, they work by repeated addition. And exponential functions work by repeated multiplication. So in general, if I want to make this a little simpler, I'll just put addition here and multiplication here. Linear functions work through addition, exponential functions work through multiplication, and logarithms undo exponential operations. So logarithms take multiplication and they turn it into addition. Let's extend this idea a little bit. Subtraction in the linear world is division in the exponential world. So logarithms take division and turn it into subtraction. Repeated multiplication are powers, and logarithms turn that back into multiplication. And we can also think of roots or fractional powers. Logarithms turn this back into division. So this is the general idea, is that logarithms turn more complicated mathematical operations into simpler mathematical operations. So rule one, the logarithm of a multiplication can be split into adding logarithms. Logarithms take multiplication. Logarithms take multiplication and turn it into addition. So a logarithm of a multiplication can be split into addition. So for example, the logarithm of x times y is the logarithm of x plus the logarithm of y. Here we have our multiplication, and logarithms undo multiplication and turn it into addition. Now you don't lose the log. The logarithm still continues, but instead of the logarithm of the quantity x times y, it becomes a logarithm of x plus the logarithm of y. And the idea from that comes from the fact that if I have b to the x times b to the y, I can write that as b to the x plus y. Because remember, logarithms are powers. So if I have the same base multiplied with powers, there's our multiplication, I can write that as the base to the addition of the powers. Let me do an example of that. Let's look at the log of 2 times 8. That just becomes a log of 2 plus the log of 8. So that's our first rule of logarithms. Our second rule is log of a division can be split into subtracting the log of the top minus the log of the bottom. And again, that comes from our rules of exponents. The log of x divided by y becomes a log of x minus the log of y. The third rule is the log of a power. Let's see, log of a number raised to the power can be written as the power times the log. So if I have log of x to the p, I can take that p and move it down in front as a multiplication, and I get log p times the log of x. And again, this idea comes directly from if I have b to, if I have b to the x to the p, I can multiply the powers, and there's the multiplication right there, because a logarithm is a power. So an example would be something like log of 10 cubed is 3 times a log of 10. These properties of logarithms are useful for two reasons. One is they make complicated operations like multiplication into simpler ones like addition, or complicated operations like powers into simpler ones like multiplications. That's one motivating factor. That's one reason that they're useful. The other is that they allow us to combine multiple logs into a single log or to split multiple logs apart. So as an example, I could do log of x times y over z. Rule number 1 says I can split my log of x into, my log of x times y into my log of x plus log of y. And rule number 2 says I can take that division and turn it into a minus log of z. I'll do another example. Let's look at the log of 2x cubed y to the 4th. Well, rule 1 says I can write each of these. I can write that whole product as adding 3 different logs together. And then my third rule says I can bring the power on the x out front and the power on the y out front. And I can also go the other way. Let's suppose I have 2 log x minus log y minus 1/2 log z, and I want to write it as a single logarithm. I can use, well, first I'll use my power rule in reverse. So this becomes log of x squared minus log of y minus log of z to the 1/2, which I could write as the square root of z, because logs turn roots into divisions. Yeah. And then I can use my addition and subtraction of logs to write this as log of, well, the log of x squared is positive, so the x squared goes in the top. The log of y is negative, so the y goes in the bottom. And the log of square root of z is negative, so the square root of z goes in the bottom. Using these rules of logs, I can open up a log, or I can collapse it. Now there's another rule of logs. It's more like a fact than a rule, but it's log base b of b will equal 1 for any base b. So, for example, log base 3 of 3 equals 1. Log base 1/7 of 1/7 will equal 1. And this just comes from the fact that a logarithm is a power, so 1 is the power that goes on 3 to get 3. 1 is the power that goes on 3 to get 3. That's equivalent to log base 3 of 3 equals 1. And then another fact to memorize is log base b of 1 equals 0 for any base b. So for example, log base 7 of 1 equals 0. Log base 1/3 of 1 equals 0. And this comes from the fact that, again, 0 is the power because a log is a power. So 0 is the power that goes on 7 to get 1. 0 is the power that goes on 7 to get 1, which is equivalent to saying that log base 7 of 1 is 0. And there's one more fact that's worth remembering, which is log base b of 0 is undefined for any base b. Because a log is supposed to be a power, and I would say, what power goes on b to give me 0? You can't get 0 through exponential functions, so log base b of 0 is undefined. Now, so far, I haven't, other than this last page, I haven't worried about what the base of my log is, right? I just wrote log. I didn't write log base 3 or log base 10 or log base b. And that's because these rules of logarithms work no matter what the base is. There's another rule of logarithms that I don't find particularly useful because we have technology. But I'm going to introduce it to you, and then I'm going to recommend that you generally don't use this rule. You just use technology. And that rule is, if I want the log base b of x, I can change it to a different base, let's say base a, with the change of base formula. Log base b of x is log base a of x over log base a of b. Now, let me give you an example. Log base 7 of 50. I can write this as log base 2 of 50, and then I divide that by log base 2 of 7. Now, this used to be super useful when the only logs we knew were log base 10 and the natural log, which is log base e. And mathematicians took the time to come up with tables that would tell you the log base 10 of almost any number. And again, the natural log of almost any number. And so if you wanted log base 7 of 50, you would go to your table and you would look up log base 10 of 50, and you would look up log base 10 of 7, and then you would do the division. But Desmos doesn't care. Desmos can do log base b for any base. And so this tool is no longer very useful anymore. And so I generally encourage you not to worry about this particular rule. A lot of rules in mathematics that we teach were developed before calculators or before flexible calculators, where you would have to use some sort of reference, like the log 10 tables, in order to answer questions. It was super important, but now we have better tools. Okay. We're going to switch gears now and solve some exponential equations. I'm going to do this very differently from the book, so potentially it will be very different from the other videos. But let's solve, for example, let's start simple. Let's solve an equation where x is trapped in the exponent. These are exponential equations. So it could be something like 2, I don't want to, how about 512 equals 2 to the x. X is trapped in the exponent. So to solve these, we're going to rewrite the equation as a logarithm, because logarithms undo exponentials. We're using the fact that logarithms are inverses of exponentials, and so they undo exponentials. So here we go. 512 equals 2 to the x. Well, I'm going to write this in words like we practiced in the previous week. X is the power that goes on 2 to get 512. So x is the power, a logarithm is a power that goes on 2 to get 512. And this is my answer. This is a number. All right. It's log base 2 of 512. That's a number. So that is exactly what x is equal to. The thing is, I don't know how big it is, right? How big is this number? And when we look at logs, we usually don't know how big they are. So to simplify this, you're going to grab something like Desmos. And in Desmos, you're going to put in, and here I will show you this time. Here's Desmos. Now, you might think you have to change the base because it's log 2, but you don't. In Desmos, you type in log, and then you use the underscore key, which is the shift hyphen next to the 0, and that moves you down, and now I can do log base 2. I use the over arrow, and I put in the argument, and there it is. The power that goes on 2 to get you 512 is 9. And therefore, x equals 9. And I can check 2 to the 9th. Yep, that's 512. So the key is to solve an exponential equation. You rewrite the equation using a logarithm, and you can do it through words. That always works. If you say what the power is that goes on the base, give you the number, then you can rewrite it as a log. There's another way I do it, and I'm going to show you that because it can be a little faster than writing it in words. So let's solve, let's see, 343 equals 7 to the x minus 1. This is an exponential equation because the x is trapped in the exponent. So I could write it as x minus 1 is the power that goes on 7 to get 343. And as a logarithm equation, that means x minus 1 is the power that goes on 7 to get 343. And then Desmos will give you this number, which is 3. So I get x minus 1 equals 3, so x equals 4. So I solved that one the same way by writing it in words, using that verbal representation, and that's a great way to do it. If you want to skip the verbal representation, there's kind of a shorthand, and that's simply to stick both sides into a logarithm where your base matches. And notice I have the log 7 of 343 just like I did earlier. And then because logarithms undo exponentials, that log and that base cancel, and it leaves me with the x minus 1. And now I have the exact same equation I did before. So I'll do another example using that approach. Let's solve. This one's not going to end up being a nice number because I'm just going to make something up. Let's say 500 equals 2 to the 3x plus 4. Now I could say that 3x plus 4 is the power, but I could also just take the log of both sides. As long as I choose the same base, then the log and the base cancel, and it gives me log base 2 of 500 equals what was in the power, because remember, logs are powers. Now Desmos is going to give me a decimal approximation for log base 2 of 500. I'll do that really quick. Log base 2 of 500 is approximately 8.97 equals 3x plus 4. Subtract 4 from both sides, and you get 3x is approximately equal to 4.97. Divide both sides by 3, and you get x equals I'm doing the calculation here in Desmos. 1.66 about. X is about 1.66. All right, so I solved this exponential equation this time by using the fact that logarithms unwrap exponentials just to cancel. Notice I didn't have to use a change of base formula because Desmos can do log of any base. I really encourage you to use Desmos when solving these. Otherwise, you're just doing more work than you have to these days. Okay, let's just do another example. This time, in our example, we're not going to be able to apply logarithms right away. We have to do a little bit of arithmetic first. Let's solve e to the 2x minus 1 plus 8 equals 24. Now, I don't want to apply my logarithm yet because although my x is trapped as an exponential, there's this adding of 8 after the exponential process. So first, I need to isolate the exponential. In this case, it's fairly easy. I'm just going to subtract 8 from both sides, and I get e to the 2x minus 1 equals 16. And now I'm ready to unwrap my exponential. This is the natural exponential base. All right, it's approximately 2.718, but that decimal goes on forever and never repeats. And the logarithm for the natural exponential base, the log base e, we write as ln for natural log. So I'm going to take the natural log of e to the 2x minus 1, and that equals a natural log of 16. The natural log and the base e cancel, and it gives me 2x minus 1 equals natural log of 16. I could get a decimal approximation for this, but I don't really feel like it. That's a number. I happen to know that number is somewhere between 3 and 4, but it is a number and I'm good. I'll leave it that way. So now I'll solve for x. Add 1 to both sides. I get 2x equals natural log of 16 plus 1, and then divide both sides by 2. And I get x equals natural log of 16, then plus 1, all divided by 2. That's the answer. I don't have any idea roughly how big that number is, which again is the whole purpose of decimals. It gives humans a general idea of roughly how big a number is. And I'll go ahead and over here in Desmos, while you can't see, I'll calculate what that is. Natural log of 16 plus 1 divided by 2 is approximately 1.89. That means if I want to get my original equation, x to the 2x minus 1 plus 8, if I want that to equal 24, the value for x needs to be about 1.89. All right, we have solved equations where the x is trapped in the exponential. Now let's solve equations where the x is trapped in a logarithm. Let's solve a logarithm of x plus 1. Oh, sorry, I have to pick a base. Let's do log base 3. Logarithm of x plus 1 equals 4. Well, again, I can write this because I know a logarithm is a power, so that means 4 is the power. That goes on 3 to get x plus 1. So 4 is the power that goes on 3 to get x plus 1. And now my x is no longer trapped in a logarithm. Calculator will tell me that 3 to the 4th is 81. Subtract 1 from both sides, and I get that x equals 80. So rewriting your logarithm as an exponential will free the x plus 1, will free what was inside the logarithm. And I could do this another way. I could solve log base 3 of x plus 1 equals 4. My shorthand way for this is just, let's stick them both up in a power, because remember, a logarithm is a power. So I made exponentials. It looked like I just drew 3's there, but what I did is I made it 3 to the log base 3 of x plus 1 equals 3 to the 4. And exponentials and logarithms cancel, and I'm left with x plus 1 equals 3 to the 4, just like I did when I rewrote it using words. X plus 1 equals 81, x equals 80. So you can free your logarithms either by rewriting them as logs or by sticking them into the power slot in exponentials. And then the exponential and the logarithm cancel. Let's just do another example. Let's make it a little more complicated this time. Let's solve log base 4 of x plus log base 4 of 3 minus 2 equals 1. So I've got a couple of things going on here. First of all, I got a couple of logarithms, not just a single logarithm. And second of all, I've got some other numbers. So first, I'm going to need to isolate any logs. And I'll do that by adding 2 to both sides. And that gives me log base 4 of x plus log base 4 of 3 equals 3. Now I have to condense or combine the logs into a single logarithm. Using my log rules, when I have 2 logs added together, I can write that as the product of what's inside the logs. And usually if I have an x times 3, I'm going to write it as 3x. So my original equation, log base 4 of x plus log base 4 of 3 minus 2 equals 1, doing some arithmetic and then using some rules of logs, it's the same equation as log base 4 of 3x equals 3. And now I can use my, I could write it in words, or I can say, there's my base 4, so I'm just going to turn each of these into an exponential, and then the 4 and the log cancel, and it gives me 3x equals 4 cubed. 4 cubed is 64, so x equals 64 over 3. And that's how you solve logarithms. Both of these work specifically because logarithms and exponentials are inverse functions. So you can always unwrap a log with an exponential, just like you can unwrap an exponential with a log. All right. Thanks for watching.